We're going to quickly recap what you need to know for your midterm in terms of atomic structure, specifically how electrons are described. And we started this lesson off talking about the wavelength properties of light. We have the speed of light is equal to the product of the wavelength, that's lambda, times the frequency, that's nu. So when you have a light of longer wavelength, let's say red light, compared to a light of shorter wavelength, let's say blue light, the red light will have longer wavelength and a lower frequency than the blue light, which has a shorter wavelength and higher frequency. In other words, wavelength is inversely proportional to frequency. When one goes up, the other goes down. We also learned that the frequency is directly proportional to the energy of the light. And Max Planck determined that it's by his Planck's constant, or energy is quantized. So in our story of the atomic model, we left off with Rutherford's model in the previous unit, and his model, although it was a big improvement from his Professor Thomson's plum pudding model, he proposed that the atom is mostly empty space and came up with the nuclear atom. It had trouble explaining why a certain material, when heated, gave off color. His model couldn't describe the chemical properties of elements, so we needed a better model, and that's where this unit actually started, was with Bohr's model. And what Bohr proposed was he was looking at the quantization work done by Max Planck and Einstein and proposed that electrons could also be quantized in these energy levels. So what's important to know from Bohr's model is that when an electron in Bohr's model absorbs a quantum amount of energy or more, that electron can move from a ground state to an excited state. And when that electron returns to its ground state or transitions to a lower energy state, will release or emit energy in the form of light. When I say light, I don't mean visible light necessarily. I mean the electromagnetic spectrum, radiation. All right, so just one important factor here is the greater the electronic transition, the greater this transition is, the greater the frequency of light, and hence the greater the energy emitted. So using Bohr's model of how electronic transitions have to be quantized, scientists can explain a phenomena they long observed, is that when an electron in a hydrogen atom goes from energy level 3 to 2, it emits a wavelength of 656 nanometers, which corresponds to the red wavelength that they observed when they passed light from a hydrogen lamp through a prism and didn't get a continuous spectrum, rather they got these discrete colors. And when an electron transitioned from energy level 4 to energy level 2, that would emit a frequency that matches the green light that they observed. And when the electron went from 5 to 2, that electronic transition would produce a wavelength of 434 nanometers. And then an electronic transition from energy level 6 to energy level 2 will produce the highest energy photon, corresponding to 410 nanometers, that purple line that you would always see when you pass light from a hydrogen lamp through a prism. So one very important thing to know from this is to understand that every element produces a unique atomic emission spectra. You can say it's like the element's fingerprint. And scientists are able to use this information to identify unknown substances by matching them up with spectra lines of known elements. And this has to do with the unique combinations of electrons and protons in each element or ion. Now, Bohr's model had limitations itself. It only worked with systems with one electron, like a hydrogen atom. So we needed something to take us farther. And that's where we got into the quantum mechanical model. Schrodinger's came up with a set of equations to describe the behaviors of electrons. And rather than having electrons in discrete orbiting paths like Bohr and Rutherford, he described electrons as being in clouds of probability, which we call orbitals. So we get 4 quantum numbers from his set of equations. And the first quantum number is n, which describes the radius or the energy of the orbital. Or simply put, you can say it's the energy level. And then the second quantum number is L. It's also known as the angular momentum quantum number, and that tells us the shape. So here's an s orbital. It's spherical. Here's what a set of p orbitals might look like. And here is what a set of d orbitals might look like. And here's what a set of f orbitals might look like. So the second quantum number, which comes from his Schrodinger's equations, describe, you can say, the shape of the orbital. The next quantum number is the magnetic quantum number, tells us the orientation of these orbitals, or how many different ways they can face. So we have 1 s orbital, 3 p orbitals, 4 d orbitals, and 7 f orbitals wherever we have these orbitals available. So here's a screenshot of one of our boards when we learned this. Gives you an overview of the types of orbitals that are available and how many at each energy level. So you can see every energy level starts with an s orbital. Every energy level has one of those. And then starting from the second energy level on, you all have a set of 3 p orbitals available. And then starting from the third energy level, you have a set of 5 d orbitals. And starting from the fourth energy level, you have a set of 7 f orbitals. Again, all of this comes from Schrodinger's equations, which we went into more detail when we learned about this. The last quantum number doesn't come from his equation, but it comes from experimental observations, and that is the spin of the electron can have one value and an opposite value. Sometimes we'll say clockwise or counterclockwise spin. So now that we have this information, we can configure electrons in atoms. So when configuring electrons, we need to follow 3 rules. So the Aufbau principle says we need to fill from the lowest energy level first, or the lowest energy orbital first. In other words, just follow the periodic table. And then the Pauli principle, I'm just going to draw it, I don't feel like writing all those words, states that you can't have more than 2 electrons in an orbital. And if you do have 2 electrons in an orbital, they have to have opposite spins. And that's because no two electrons in an atom can have the same set of quantum numbers. And then finally, we learn Hund's rule, which states that when you're filling electrons in degenerate orbitals, or orbitals with the same energy, each electron gets its own orbital spinning parallel before you pair them up. So these are illustrations, or this is an illustration of Hund's rule. So you can expect to see on your midterm possible violations of any of these rules, and that you'll have to identify. So you also have to know the names, as well as recognize the violations. So when you're configuring electrons, when you see a periodic table, you should see this. You're not going to get this, but you should see it, where you have the first 2 columns representing the S block, the last 6 columns representing the P block, the transitions metals representing the D block, and the intertransition representing the F block. And the number of columns in each block match up or align to the number of electrons that go into those orbitals. So let's say you're asked to write the electron configuration for titanium, which is number 22 right there. you would start with a 1s orbital. You'll put 2 electrons in there. So it would be 1s2, followed by 2s2, followed by 2p6. Again, these superscripts represent the number of electrons in those orbitals. It's not a mathematical function. 3s2, 3p6, 4s2, and then titanium is in the first, second column of the 3D block, so it's 3D2. Now, more preferably, and we'll probably ask you to write all of this in noble gas notation, so you go to the previous noble gas, which in this case is argon, put that in brackets, and then write the remaining, which is 4s2, 3d2. If you want to rewrite this with the 3's coming before the 4's, that's fine, but this is also acceptable. So for many students, it's easier to just use this Aufbau filling chart, which you'll also have on your reference sheet.